Differential equations. There's a whole class you will be taking called differential equations. Moreover, there will be a sequence of classes: ordinary differential equations, ODEs, and partial differential equations, PDEs. Those equations are one of the most important parts of mathematics if you planned to go to the STEM major and use mathematics in some kind of applications like engineering, physics, and so on. Differential equations are basically equations that involve, guess what? Derivatives. So they involve sometimes original function and derivatives in the same equation. You will see it in a second. And we're going to be teaching you how to solve these. And there are so many types of differential equations. That's why you need years of education to actually learn how to solve them all. But in Calculus 1 class, we like to introduce at least the simplest case when you just need to find entire derivative and plug some numbers to be already smart enough to find, for example, the position from the given velocity or acceleration, and so on. One more thing I want to introduce is initial value problem. I call them IVPs, initial value problems. Those are the problems that have differential equations usually, and they have some initial value given. So some kind of initial information is provided. Given initial values. And by initial values means some kind of original record is given. For example, if you are working with the bacteria, and this is your petri dish. Let's make it more like a circle. A petri dish is that piece of glass. Inside you have little bacteria and they are dividing. Remember all those kind of things they show in fancy movies and so on. So if you have recorded that at 12:13 p.m. you had exactly 4 bacteria, then this is the initial value at some initial moment, and any initial moment can be initial. It may be 00 time or maybe at the time you recorded the information. Then you can use this initial value to create the initial value problem to look into the future and tell people when you will have 1 million bacteria if at 12:30 p.m., 13 p.m. you had 4 bacteria with the given rate of division, or vice versa. Maybe now in front of you, you see 1 million bacteria already developed. With initial value, you can find the rate, how fast they were developing, if you know that 4 hours ago, it was just 4 bacteria. Make sense? One more example, and we're going to go through this example, is the example of rectilinear motion. When a particle is given and it moves away in a straight line. We want to find its position, the position function, let's call it s of t, from the given, and now I can give you, say, velocity, right? Then you integrate the velocity to find a distance, because you remember the derivative of distance gives you velocity. But I can also give you acceleration, and you will see what's the problem here. It's not that simple. Find its position function s of t if given. Let's do like this. If given, and we give you acceleration, an acceleration function. Acceleration function was recorded or created from some data. For example, a of t is 6t plus 4. That's a line, actually. Then, what's the problem? I can just integrate this function twice, right? If I integrate it once, it will give me velocity, because the derivative of velocity is acceleration. If I integrate it twice, it will give me a position function. That's it. We solved the problem. However, every time when you integrate, you will have plus c every time, right? And that plus c gives you a family of solutions. And that's not good, because I want to have exact answer. I don't want to have a family of answers. That doesn't make sense to provide with someone a family of answers for a particular question. I want to know the position function for this particle that moved away in a line if I record acceleration. I don't want to have millions of answers. The answer should be unique. And that's where the initial values come in. Initial value problem, or I would even say initial value, it's fine. Initial value problem gives you initial velocity. That means at some point I recorded that velocity at time 0 was -6 centimeters per second, if you want to have units. And also I recorded initial position function or displacement. Initial displacement. The function s at 0 was 9 centimeters. So those initial values are part of the initial value problem, IVP. And now we're going to start solving it. Solution. Step 1. First, you need to know the idea. The idea is that from the distance or position function, we can go into and get velocity by differentiating the position function. We knew that. And then from there, we can go into and get acceleration function by differentiating velocity, or it's a second derivative for displacement. So if I want to go back, and that's exactly what I'm doing here, from acceleration, I need first to integrate or find the first antiderivative to get to velocity, and then I will integrate and get to position function. Make sense? So I will find antiderivative, and one more time, antiderivative. Instead of differentiating, basically I'm doing differentiation. That's the whole idea. Let's start doing that. First, I am given acceleration. Let's put it in the box. Here it is, you can see it. To find acceleration, to find velocity, v, since I know that v prime gave me acceleration, and acceleration is 6t plus 4, that's known. That's what I know. I would do like this, since. Then, how to find v? V will be antiderivative or integral, right? Indefinite integral of a of t. And now what should I do? What should I write at the end to close the integral? Who's at dx? No, it should be dt. This variable should show you over here with respect to which variable we are integrating. Since we're integrating with respect to t time, then it should be integral function dt. Then it means I'm integrating 6t plus 4 dt. Now we learned how to integrate fast, and the answer will be, what is integral of 6t? Can you say? Maybe you should practice a little bit more to be fast at this. I promise you that in a couple of weeks you'll be a pro in this topic. It will be 6t squared over 2. Why? Because this is t raised to the 1, and the power rule says increase the exponent by 1 and divide by the result. So the new exponent will be 2 and divided by 2. Multiplied by 6, because it's a constant standing in front, multiplied by the function. Plus, integral of 4 will give you 4t. Just remember, it will be much faster if you remember. Integral of a constant gives you constant t. Or it's basically 4 empty integral. An empty integral gives you a variable t. Plus c1. I will call it c1 because we're going to have several c's since we're integrating several times. Now, let's simplify. It will be 3t squared plus 4t plus c1. And this is what we call, since we have c in the answer, this is called general solution. General solution. The general solution, if we were asked to find the velocity, seems like a family of functions. Family of functions. And we know what kind of functions they are. Those are actually parabolas. And what is happening here is I can draw all of these parabolas. Well, not all of them, of course. But basically, those are some kind of parabolas looking like this. One, and one more, and then one more. If c is negative, it's going down. The more negative c, the more it keeps going down. So it's a family of functions, family of solutions for the velocity function. But I want to have a unique one solution. To have that unique one solution, I will use initial value. Initial value will capture only one solution, maybe this one, or maybe this one. All of these are the same parabolas, but shifted up and down by c. The particular c that comes from the particular data, for example, you, the one who was watching the particle moving, and you recorded that, putting it in the box. At the time 0, the speed of this particle was -6. By the way, what does it mean to have negative speed? Indeed, it means something, the distance is decreasing, right? Because velocity is derivative of distance. Negative derivative means the distance is decreasing between me and you. So, this value will capture one of those functions. Well, to capture one of those functions, I will write down this way. To find that particular c, to find c1, use initial value. And initial value is v at 0 is -6. On the graph, it will look like this. When t is 0, and this is the v of t, family of functions, when it was 0, the output was -6. Say this is the one. Since I know this point and only one unique function goes through this particular point, I can fix this one unique answer. I can identify this unique answer from the whole family of functions. That's the trick. So basically we fixing the unique solution using IV, initial value. Make sense? Because they are all parallelly shifted up and down, only one of them can cross this original unique initial value. So, if I know that v at 0 is -6, how should I find this solution? How should I find this c? I need to find the c, and then if I find c, I can write down the unique v function. Just plug t equals 0. Why t equals 0? Because this is what it means. At t equals 0, the answer is -6. So I'm plugging t equals 0 and v equals -6 into v of t equation. And let me call it somehow. Since it's pink, I will call it star over here, into the star. So the star says v of t is 3t squared plus 4t plus c1. That's my star. Now, v of t is -6. That's the output. And then I'm plugging 0 everywhere I see t. Right? And now I can calculate, or basically solve for c2. c2 is 0 plus 0 plus C2 is negative 6. So C2 is negative 6. Please don't think that this is the case all the time, because in your homework you will see quite a lot that the constant is matching the initial value. That's not always the case, especially with exponential function, logarithmic function. If I plug 0 into something like this, that is not 0 at 0. That is actually 1, right? So don't make this mistake and always assume that whatever initial value we give you, that will match with the C value. Oh, why it's C2? It should be C1. Fix it. Should be C1, I just noticed. So we found C1. Why did we do that? We can say thus, the unique particular solution is V of t equals 3t squared plus 4t minus 6. Put it in the box. That's not the final answer. That's just velocity. But at least we can say that this is particular solution. Particular solution of initial valued problem, IVP. That was just step 1. I will break it into step 1a. 1a, find derivative. 1b, plug the initial value to solve for the c, constant c, and then get the result. Step 2, we actually are asked not for velocity. We are asked to find distance. Remember the position function s. Well, I can say that we know that s prime of t gives you v of t. Let me repeat the whole idea. V of t now is found, so we know that. Known. Or I would say we found it. Right? So we did it. We did it. We did it. Anyway. Then s will be an integral one more time, but now of the different function. 3t squared plus 4t minus 6. What should be at the end? Right, dt. Integrating 3t squared, it gives you 3t cubed over 3, or you can just remember it's t cubed, plus 4t gives you 4t squared over 2 minus 6t, and now I have plus c2. That's a new constant. Let's simplify. 3 cancels 3, gives you t cubed, which makes sense. Derivative of 3t squared indeed is t cubed. 4 and 2 gives you 2t squared, and that makes sense. If you differentiate 2t squared, it gives you 4t. Minus 6t, which makes sense. If you differentiate minus 6t, it gives you minus 6. Plus c squared, derivative of c squared is 0. So we know we did not make a mistake. Let's put this in the box and speed up a little bit. This is my general solution. General solution, family of functions. And if you want to see how these look like, these are all cubic functions. Remember how the cubic function look like. If not, check out my video, common functions we expect you to know. So that is my s of t, right? I will even write down over here, s of t equals s of t. So it seems like the distant function is a family of cubic functions. And they all look like chairs. A chair, cubic function, a chair, one more and going up, and so on, right? So cubic functions. How to fix one particular cubic function? We need to have a point. If the point is over here, I know the top function is the one we need. If the point is over here, I know the bottom function is what we need, and so on. That point is given by the initial value. So that's going to be 2b, 2a, 2b. To find C2, use initial value. But in this case, for s, right, for distance, go back into the problem and you will see that we told you that s of 0 is 9. That means when particle started moving at time 0, the thing here inside is my t, time 0, When particles started moving, the object was already 9 centimeters away. 9 centimeters away. That's the idea. So I can try to locate this point on my graph. At 0, I have point, say it's over here, 9. So that's at 0, t equals 0. The height is 9. That's how I know that this is the function I need to fix. This is the function I choose as the particular solution. This particular solution was chosen from the family of solutions. General solutions. From the general solution, we're choosing particular solution. I'm plugging in, so plug t equals 0 and s equals 9 into double star. And I will call double star this orange piece over here. Star and star, star and star. Plugging in over there. S of t equals t cubed plus 2t squared minus 6t plus c2. Well, s is 9, so 9 equals t cubed, that's going to be 0 cubed, plus 2 times 0 squared minus 6 times 0 plus c2. And again, just by a coincidence for this particular case, c2 happened to be 9. That's not the general rule. So don't skip the calculations. You actually have to calculate it. But yes, it did match again with the initial value. Then I can write down the formula. And that's actually the final answer. S of t equals, look at the double star, t cubed plus 2t squared minus 6t plus, instead of c2, now I'm talking about 9. That's the final answer. Why? Because we found the particular solution, from the family of solutions. How did we find this s of t? Let's review really fast the whole problem. We had originally acceleration, we integrated acceleration and we got velocity, but a constant popped out, c1. To find that constant, we plugged initial value for velocity because we had a record that velocity at 0 was -6. Then we found t2. When we found t2, we had a full complete equation for the velocity. We integrated velocity and that gives us s of t, the displacement, right, or distance. But one more constant popped out and I called it c2. To find c2, I had to use initial value for the displacement. Well, luckily we had a record that s of 0 was 9. I plugged 0 everywhere and I knew that the answer should be 9. Here it is. Left hand side equals 9 equals 0 everywhere where t is, plus c2. I solved for c2. When I found c2, the final answer is here. S of t is a cubic function, t cubed plus 2t squared minus 6t plus 9. And that's a particular final solution. Great job. Keep working on these problems and you will see that actually they are pretty enjoyable. They have the same logic every time and you barely have any surprises here. See you next time.